In this tutorial, we will be discussing dynamic equilibrium and the equilibrium expressions. A system at equilibrium is one in which the concentration of reactants and products remain constant. The rates at which the substances are being consumed and made are the same. That doesn't mean the concentrations are the same. It means that the rate in which it happens is the same. Systems at equilibrium are dynamic in nature and reversible. We've discussed dynamic equilibrium in the past. But as a reminder, it's conditions where the forward rate of the reaction is equal to the reverse rate. That's where the word equilibrium comes from. At equilibrium, the rates of the forward, Kf, and reverse, Kr, reactions are equal. This does not mean the concentrations of the reactants and products are equal in value. The reaction may reach equilibrium only after most of the reactant molecules are being consumed. If we look at this graph down here, we have reactants here, and we have the products here. At the beginning, we have a lot of reactants, and we have 0 products at the very, very beginning. And then as the reactants are consumed, the products are made. If the equilibrium favors the products, a lot of the reactants are going to be used before it hits that dynamic equilibrium point. So this indicates that the position of equilibrium favors the formation of the products, because we have lots of products here and very little reactants because they've all been converted. Reactions that reach equilibrium when only a small percentage of the reactant molecules is consumed. This indicates the position of equilibrium favors the reactants. Okay, so right now our dynamic equilibrium point is right here. But what if it were over here? Once again, we start over here where we have lots of reactants and no products. But let's say instead of having it go through the system and make lots of products, maybe it only made this many before it started going back and forth. Well, that would mean it was favoring the reactants. It doesn't want to go forward. It wants to go backwards. And that favors going to the left of the reaction. At the beginning of a chemical reaction, the forward reaction rate is favored. The reactants going to products dominates. The reactant concentrations decreased and product concentrations increase over time. As reactant concentration decreases, the forward reaction rate slows down. So as we get less and less and less things colliding, we get less and less and less products being formed. That's what they mean by it slowing down. A chemical equation at equilibrium, the forward reaction rate is equal to the reverse reaction of the rate. Does not mean that those concentrations are equal. We've said that several times now. Reactants going to the products are the same as the products going back to the reactants. The products can react to reform some of the reactants, assuming the products are not allowed to escape. Processes that proceed in both the forward and reverse direction are said to be reversible. So in other words, if they're able to go back and forth, they're reversible. The relationship between the chemical equilibrium of the reaction and the concentrations of reactants and products is called the law of mass action. This is a ratio between the products and the reactant concentrations. So if we have a generic chemical equation here, this ratio is going to be written with the products over the reactants. So it's always the right side of the equation over the left side of the equation. These little a, little b, little c, little d, those are the stoichiometric coefficients. Unlike the rate law, stoichiometry goes into the equilibrium constants. So we actually use these numbers in the solving equilibrium constant. So here's our constant K. We have C and D on the right hand side. So the concentration of C, concentration of D. Remember that box is abbreviation for concentration. Little c, little d for the coefficients. That's divided by the reactants with a concentration of A to the little a, concentration of B to the little b, because that's on the left-hand side of the reaction. And K is the equilibrium constant, which is different for every chemical reaction at a different temperature. So we can practice these. We always want to take the right side is on top over the left side, which is on the bottom. So NO2 to the 4th power times O2. I'm making those boxes because those are the concentrations. There's no coefficient here, so I leave it blank. Over into O5 to the 2nd power, and that is equal to K. K is equal to the right side over the left side. The products are CO2 with no coefficient, CF4 with no coefficient, and COF2 with a coefficient of 2. And finally, NOBr with no coefficient, NO, no coefficient, Br2, this is a coefficient of 1/2, that's perfectly fine, we just put a 1/2 right there. That just means we're going to take the square root of it when the time comes. And that once again is equal to K. Pure solids and pure liquids are substances whose concentration doesn't change during the course of the chemical reaction. Note, their amounts can change, but the amount in the solution does not, so that's why the concentration doesn't. Because their concentration doesn't change, solids and liquids are not included in the equilibrium expression. If we look back up here, every single one of these were in the gas phase. They need to be either gas or they need to be in aqueous phase to be included. For example, if we take this equation, A plus B yields C plus D, A is a solid, C is a liquid, so we do not include those in the equilibrium constant. So the right side over the left, there's D to the D power, B to the B power, because those are both aqueous. So here's another visual. Even though the carbon is increasing, none of it's floating around in solution here. So there is no actual change in the concentration. So remember, solids and liquids are never appear in the equilibrium equation. So here's another example. Because water is liquid, it is not included here. We have NH4, OH minus, and NH3, and that's it. On this one, the right-hand side is SO2. The left-hand side is O2. Sulfur was not included because it's a solid. So let's explore the relationship of the equilibrium constant and the chemical equations. For the reaction A plus B yields C plus D, the equilibrium expression is the C and D over the A and B. C, D, the right side over the left side. But what about the reverse reaction? Because remember, these are all reversible. They go one way, they go forward, and they also go back to the left. So let's say it's going the reverse. Then suddenly the A and B are on top, and the C and D are on the bottom. So note when the reaction is written backwards, the equilibrium constant is inverted. So the K of the reverse is the same as 1 over the K of the forward, because they're reverse of each other. Only equilibrium concentrations of molarity or pressure in ATMs values are used in an equilibrium expression. The equilibrium constant K of C is dependent on temperature, numerical value in the stoichiometric specific, and it is unitless. Numerical value of K of C indicates whether or not the chemical reaction is product favor or reactant favor. With the reaction at equilibrium, the value of K is a lot greater than 1 if it's a really big number. there will be more product molecules present than reactant molecules. So if we think about it this way, we know that K is always the products over the reactants. If K is big, that means this number up here is big. So that means that you're creating lots of products. That's why it favors the products. It favors the forward reaction. If it's really small, that means the reactants are a big number. So that means it's getting divided by a really big number. So that means there's more reactant molecules present than product molecules, which means it favors the reactant. So it favors the reverse reaction. So here's a visual. If the product is favored, here's our HBr molecules. Notice that there's a lot more HBr molecules here than the H2 and Br. So this number up here is bigger. So that's giving us a large number. Here's the NO molecules. There's far fewer of these. So this number up here is small. These numbers down here are much bigger. So a small number divided by a big number is giving us a small number. So let's write an equilibrium expression and indicate whether the reaction is reactant favored or product favored. So it's always the right side over the left. And that is equal to 8 times 10 to the 25th. That's a really big number. So therefore, it's going to be product favored. Meaning it's going to prefer the forward reaction. The next one the products over the reactants is equal to 3 times 10 to the negative 17. Negative 17 gives us a really small number, which means the reactants are favored, which means the reverse reaction is actually the one favored. And those are your equilibrium constants.